Hello everyone, so let's continue our conversation on chemical equilibria and looking at some general questions on that topic. In this example, I want to look at how we can calculate some equilibrium concentrations given a Kc value and a specific mixture of reactants. So we're told consider the reaction of carbon monoxide and water vapor, and it forms an equilibrium with carbon dioxide and hydrogen gas. And it says, suppose that 1 mole each of carbon monoxide and water is placed in a closed 50-liter reactor at 1273 Kelvin, and then Kc at this temperature is 0.58. Determine the equilibrium concentrations of all species in the system. Right. So before we get to that bottom part that you saw there, let's first analyze what we have. So we're told that we initially mix carbon monoxide. So, you can say carbon monoxide initially or carbon monoxide zero. So meaning initially we mix the same amount of carbon monoxide and water vapor. So that is 1 mole in a 50-liter reactor. So the concentrations of these is 50 mole over 50 liter, 1 mole over 50 liter. That is 0.0200 molar. All right, and those are the reactants. We're not told anything about the products, implying that our product concentrations initially are 0. So the CO2 and the H2 concentrations initially are 0 molar. All right, great. So that is our initial analysis. Now, to get the concentrations at equilibrium, we of course then use an ICE table, or ICE table. So meaning we look at what is our initial concentrations. So that is 0.0200. Both of them are the same, and is 0 for our products. All right, then what is the change in each of these species? Now, it should be quite obvious that we mix a set of reactants. So in other words, the reactants should decrease in concentration to form an equilibrium, and the product concentration should increase to form an equilibrium. But the more formal way to do it is to test whether or not what is the reaction quotient. So just to double check, it's glaringly obvious, but I like to do it this way to get you in the habit of it. So let's write the reaction quotient, and I hope you're very comfortable with writing these type of things now. So the reaction quotient for this reaction is that, right? Hydrogen and carbon dioxide are the products, carbon monoxide and water vapor are the reactants, so they go in the denominator. And if we plug this in, well, very shockingly, both of these at the top are 0. At the bottom, we see 0.02 and 0.02, and this gives us a value of 0, which is indeed less than Kc, which is 0.58. This means that Q is less than Kc. And when Q is less than Kc, it means that the forward reaction is favored. Forward reaction is favored until equilibrium is reached. Therefore, it means that our product concentration is going to increase and our reactant concentrations must decrease for equilibrium to be established. And hence, in other words, let's make that link. So remind yourself that that gives us what needs to happen with the change. So that means we need to lose minus and plus and plus. We can put the x's down, whatever the amounts are. We see that all of them are in a 1 to 1 to 1 ratio, so it means all of these are 1x to each other. If there were 2x or 3x, then remember 1 to 3 to whatever the stoichiometric ratios were, then you would have put those stoichiometric ratios in front of the x's, right? Because x is the amount that each of these decrease by or increase by to reach equilibrium. Okay, so once we know what the initial is, what their change is, then we can calculate what is the amount each of these are at equilibrium. So meaning that for this must then be its initial minus x, because meaning it is the initial minus x. So the change is it decreases by the amount x. The same for the water vapor. It must decrease by the amount x. The CO goes from 0 and increases by the amount x, so hence at equilibrium it is just x, and the same for the hydrogen. It is the amount x at equilibrium. So now we know what the amounts are at equilibrium. But what we are interested in is actually what the physical quantities are. So we need to solve for this x value to get the physical numerical values for this. And what we can do to calculate or to get this numerical value for x is use the Kc value, because Kc has a physical value, 0.58. So let's write Kc. So Kc is equal to 0.58, and that must be equal to the equilibrium constant expression, right? Which is again equal to these concentrations at equilibrium, right? So let's just make a note for ourselves. This little block here, for example, is CO at equilibrium, and this block here is water vapor at equilibrium, and this block here is CO2 at equilibrium, and this one here is hydrogen at equilibrium. Right, so now once you've reminded yourself of that, let's put them in their places. So each of these, you can see CO2 at equilibrium has a value of x, hydrogen has a value of x, CO has a value of 0.0200 minus x, and water vapor has a value of 0.0200 minus x. Okay, maybe extend this line a little bit. All right. We can also simplify this a bit further. At the top we get x squared, and at the bottom we also see we have the same thing multiplied by each other, so it's 0.0200 minus x squared. And because both things are squared, the numerator and the denominator, that means we can actually write it as x divided by 0.0200 minus x all squared. This in general is something that you can look out for when you're doing these type of calculations, because it simplifies your calculations a lot. You can of course go and multiply this out if you wanted to, but look for anything that you can simplify to make your life a lot easier. Okay, so let's maybe just write this a bit more explicitly so that we can see, because remember this whole expression is now equal to 0.58. So that means in principle that x divided by 0.0200 minus x squared is equal to 0.58. So we can take the square root, right? So take the square root of both sides. That means that x divided by 0.0200 minus x is equal to the square root of 0.58. And now it's a bit of algebra. So then you should get x equals to the square root of 0.58 multiplied by 0.0200, and then minus the square root of 0.58. I'm just going to squeeze that in there, multiplied by x. Alright, and now we solve for x, so I'm going to take that to the other side, so that should become then 1 plus the square root of 0.58 multiplied with x equals to square root 0.58 multiplied by 0.0200. Of course, you can plug this into your calculator. This just makes it a bit easier to calculate in one step now. Alright, so now you can say the square root of 0.58 multiplied by 0.02 divided by 1 plus the square root of 0.58. And I got 8.646 times 10 to the negative 3 molar. Alright, so that is the value of x, and that of course has to be molar because we worked in molar in our ICE table here at the top. Okay, so now let's bring the stuff that I had here at the bottom. You can bring that a bit to the top here. So the concentration of CO at equilibrium is equal to 0.0200 minus x. And x, of course, is this value, 8.646 times to the power of negative 3. So if we put that in and we round, and it is two significant figures because k is two significant figures, I get 0.011 molar. The same for water. It was 0.0200 minus x, which also rounds to 0.011 molar. CO2 is just equal to x. So in other words, we can round the x value, and I get that should be then 8.6 times 10 to the negative 3 molar. Same with hydrogen, it's just equal to x, and you can just round it to 8.6 times 10 to the negative 3 molar. Alright, one important thing that I kind of just glossed over is why can't we make the approximation here? So why can't we say here that 0.0200 minus x is just 0.0200? If you compare Kc with so times 100, and you compare that with the concentration of CO and CO0 and hydrogen at the start, then you will see both of these values, which are 0.0200, and Kc times 100 is 58. That is much larger than 0.02. In other words, it is very much significant. This x here is quite significant when you subtract it from 0.02. And you can see that in this calculation here, that if you subtract this x from 0.02, you get something that is significantly different from 0.02. If we were to do this calculation in the end, and we got, after the rounding, we actually got the same answer, it would have meant that we could have actually have done the approximation. That's in general your test. If you did the approximation and you got the same answer that you got at the top, then yeah, that's an indication that yeah, you could have done the approximation. So yeah, so that's why I didn't do the approximation, but remember, you can always test whether or not the approximation will work. But in general, the approximation only works with very small Kc values, so that's the only time when it's really relevant to test it. But you can always test the approximation just to, you know, as a good step, just as it's good to always calculate Q, and well, you should always calculate Q, test for the approximation, and then calculate your equilibrium values. Alright, I'll see you in the next video. Thank you for watching.